So we see that 8/3 is exactly what we expected, right? If this is the actual area of 8/3 now, 8/3 does fall out between 1.75 and 3.25. Because 8/3, I guess, is like 2.6 the line over, right? It's 2 2/3. So that's comfortable, right? It's comforting, I guess I should say. It's comforting that our value came and was between the lower approximation and upper approximation we had before from the pictures. We anticipate this should be the case. So the actual area of 2.6, the line over it, okay, 2 2/3, is the green area here alone. No overestimation whatsoever. All this has been shaved away, in a sense, as the rectangles became thinner and thinner, and more, an infinite number of them, in a sense, were filling up the area between this curve and the x-axis. So there's our 8/3. There's our answer. Got it. So this gives us a powerful technique now. We can use the definition of the integral, this limit definition, to calculate exact areas. We don't have to approximate anything anymore. We can always calculate exact areas now. Analogously to whenever we were calculating derivatives approximately, and then we had a definition that allowed us to do it exactly. So to now, with areas, we had methods, right? The Riemann sums, the approximations here to get things approximately, and you could refine it with having more and more rectangles, but you never had exactitude, right? But now you have exactness with the limit definition here of the integral, and you can use it to calculate these areas. But as you saw with the limit definition here, and as we knew with the limit definition of the derivative, it become very cumbersome sometimes to calculate these areas. Right? And this is actually a fairly simple example I chose on purpose, so this would not become too convoluted down here. It can get very difficult very quickly, and sometimes impossible in a sense, because of the difficulties of computation and the limits on our brain power. So that gives us some impetus to go ahead and start moving ahead into the next sections and be able to find an efficient way to find these areas without resorting to the actual definition as a limit. Just like with the derivatives, we found rules, power rule, chain rule, product and quotient rule, that allowed us to calculate derivatives very quickly without resorting to the definition whatsoever. So too, we would like to develop rules for taking integrals, that is finding areas, not slopes now, but finding areas between curves and x-axis, without resorting to the definition, but based solely on mechanical rules.